I am Tse Ka Ho. This is my EE3070 Final demonstration video about my small circle magnetic sensor. In this video, I will talk about the background, objective, the code, the PCB schematic, PCB layout, and challenge and cost, and the progress in this week, and the potential improvement of my project. In our underwater robotics lab, we usually use RV or AUV to do the underwater research and use the thruster of the T100 to use as the main propeller of our RV and AUV. And it is use the ESC and the PWM to input the signal to the electronic speed controller to have a precise control. However, there are some problems among the original design of the thruster, such as if there are water inertia push the thruster in another direction, then the thruster may have wrong rotation speed, although the PWM is correct. To avoid this situation, I designed a PCB with MT6701 magnetic sensor and the PID control of PWM to make the thruster will continuously to go to the correct and expected movement of the rotational speed. And then I will introduce my code system diagram. And firstly is the power line. It will convert the power from 5 volts from USB of computer or external power source up to 15 volts, convert by an LDO and convert to the 3.3 volts, and then to the power plane of the PCB and convert for all the IC. I use ESP32S3 as the main controller of my PCB and use it to control and communicate with different IC signal such as the MT6701 and the VP230, and use it connect to the antenna to complete the OTA process. My code setup is that after including library and set up the Wi-Fi and the I2C and campus, and then I will set up the multitask for 2 core. The one core is PID control of the PWM of the thruster, and it is firstly detect the angle and time, and then to calculate the rotating speed, and then to output the PID control of the speed, and then to output the PWM, and then loop again. And another loop is that receiving campus value for every 5 milliseconds. It will wait for every 5 milliseconds to get if there's a campus header package is 19, and it will get the target PWM value and then to output the value as a reference to another core to calculate the PID output of the speed. And if there is no, then it will loop again from the beginning of the loop, and then to wait the campus value again. I decide to use its incremental PID control is that it is the easiest way to control the thruster rotational speed against the noise and the inertia. After I input different PWM value to the ESC of the sample thruster, and then I use the PCB code to determine the value of the different rotational speed, and then I use them to get a linear regression to the graph, and then to use it as an expected output of the rotational speed. And here is my PCB schematic diagram of among different parts, and I will explain more in the PCB parts review. And here is different parts of my PCB, and you can see there's ESP-S3 and another things. And I want to talk about is my PCB antenna filter, and it is the 2.4 GHz antenna filter, which is using the pi type filter. And it is clearly shown that I even to simulate the parasitic resistance and the capacitance and inductance of the long wire of my PCB, and then I also use that to calibrate my gain middle is perfectly on the 2.47 gigahertz, and so the Wi-Fi is perfectly work in the OTA part. The main problem of my PCB currently is the heating problem, and it is solved by adding the small decoupling capacitors. Another problem is the soldering pad of my PCB is very easy to tear off. After my tuning PID parameter, and I can control the stop movement, input PID is 1500 to become this slow, from this oscillating and slow damping result become a very fast damping result. And you can see I use my finger to simulate a opposite direction due to the water movement. And in future, I will tune the PID parameters to let it also have a fast response against the dynamic input of the thruster movement. Thank you. This is my presentation of my EE3070 project.